So under week 6, which we're not really starting yet, but there is an outline of the lecture. Boy, that's not a very good name. Let me change that. Lecture, antibiotics. The T means something to me. We change that one too. All right. If there's no questions, we'll go ahead and get started. We're supposed to start at 2:30 and it's 2:33 now. I'm going to move ahead and start talking about antibiotics. This lesson, as well as Chapter 7, will not be on Quiz 4. It will be on Quiz 5, which will also cover Lab 7. I've got that somewhere. There we go. So we're going to be talking about antimicrobial drugs. This is always a topic that students seem to really enjoy, so hopefully you will be able, I've got the learning goals for this lesson right here, be able to define what selective toxicity is and discuss its importance to the development of antibiotics, be able to explain why new penicillins have been developed. And once you get into it, it's pretty easy why we've made a whole bunch of members of the penicillin family. Be able to describe the mechanism of action of a variety of drugs, meaning drugs don't work on all infective agents. And so we say they have a mechanism of action, how they work, and what they're good on. And we'll talk about that in this lesson. And then lastly, be able to explain or describe the mechanism of action of the spectrum of the activity of a number of antibiotics. So we'll talk about a number of common antibiotics and talk about how those drugs act, what their spectrum of activity is, and how they act. All right, any question about any of that? Everyone good? So we've talked about prokaryotes and eukaryotes, and we're going to talk about the differences between them in a little greater detail. So we've already talked about how, that should be bacteria, not eubacteria. I'll try and make a note that I'll change that in the thing. Eubacteria is an older name for bacteria. And literally it means true bacteria. And I didn't notice that that was on here. So let me put that, change eubacteria. I'll just update that after the lesson. So as we've talked, they have some differences between the bacteria and the eukaryotes, like there's differences in their cell wall and their ribosomes and some of the enzymes within the cells. And I want to talk a little bit more specifically how the bacteria differ from the eukaryotes. They differ in the size of their ribosomes. The bacteria have a smaller ribosome than the eukaryotes. And we discussed this before. Excuse me, I'm about to sneeze here. Let me go out of the screen. I'm not sure what's causing that, but I might sneeze later on. But the bacteria have what we call a 70S ribosome, and that S is the unit of where the ribosome sediments and an ultracentrifuge gradient. You don't need to know that part, but the bacteria ribosomes are a little smaller than the eukaryote ribosomes. Okay? The two also differ in whether they have peptidoglycan. Bacteria have peptidoglycan, and all of the bacteria that have a cell wall have peptidoglycan. Now you notice how I qualified that, and that is the bacteria have to have a cell wall in order for them to have peptidoglycan. And the eukaryotes, there's no cell that has peptidoglycan in them. The two also differ in their RNA polymerase. The bacteria only have one kind of RNA polymerase, whereas the eukaryotes have several kinds of RNA polymerase. The two also differ on their start codon. I think I mentioned that before. Eukaryotes, when the ribosome reads the start codon, it always codes for a methionine. In the bacteria, it codes for a related amino acid, but a different amino acid, and it's called formal methionine. And then the two, of course, differ in their response to many antibiotics, such as penicillin, like penicillin G, where the bacteria are inhibited and the eukaryotes are not inhibited. All right, any question about some of those differences? Everyone good? Well, the goal of an antimicrobial drug developer is to take advantage of some of these differences between the bacteria and the eukaryotes to develop an antimicrobial drug that will harm the bacteria, which is the pathogen, and will leave alone the eukaryote cells, meaning not harm the eukaryote cells. And that, we have a term for it, is called selectively toxic. So if a drug is selectively toxic, it will harm the eubacteria, but leave the eukaryote cells alone. And the whole goal of an antimicrobial drug developer is to find a drug that exhibits selective toxicity, where it will harm the bacteria by taking differences that the bacteria have and use those differences and then leave the eukaryote cells alone. And that is the goal of the antimicrobial drug developers. Any question about that? So that's what all the antibiotics do. They find a difference between the bacteria and the eukaryotes, and then they take advantage of that difference, and that's why they harm the bacteria cells, but they largely leave the eukaryotic cell untouched. And I said largely because there is no drug which is 100% selectively toxic to bacteria and then 0% toxic to eukaryote cells. But they are more toxic to the bacteria than they are to the eukaryotes. For example, penicillin G, the reason why it works is it's harming the formation of peptidoglycan. And so that tends to leave the eukaryote cell alone. And here's another picture of a selectively toxic drug. Let me move that out of the way. It's an antimicrobial peptide, such as maybe you've made on your skin. And it has a lot of positive charges to it, more positives than negative. And so it has a stronger attraction to the bacterial membrane because it has more negative charges on it than the membrane of a mammal cell or a membrane of really any eukaryotic cell. Okay? Any question about that? I might have unmuted somebody there. Let me see if I did that right. It looks like we're good. All right. So let's talk about the mechanism of action of the antimicrobials. Oh, wait. Before I move on to that topic, we're ignoring a whole group, a whole domain of cells. Why are we ignoring the archaea? Come on,
Because they don't make us sick.
Say again?
They don't make us sick.
Yeah, the archaea are not human pathogens. They do not make us sick. So that is why we are ignoring the archaea. And for the time being, the drug developers have been ignoring the archaea because they do not make us sick. Now, if you believe in evolution, someday in the future, there probably will be an archaea which will come to make us sick. And when that day happens, hopefully it won't be in my lifespan, we don't have many antibiotics that will work on the archaea. Most of the archaea have been taking advantage of the differences between bacteria. What did I say? Most of the archaea. Most of the antibiotics have been taking advantage of the differences between the bacteria and the eukaryotes, and then using those differences to make a drug, which we call the antibiotics, which show selective toxicity, meaning they're harming the bacteria and not the eukaryotes. There's very few antibiotics we have which work against the archaea. There are some, and we'll talk about that, probably not today, but in a later lesson. There are some that inhibit protein translation of the bacteria, and they also work against the archaea. But then drugs like penicillin and all of the penicillin family, and I think all of the antibiotics that work against peptidoglycan, they're not going to work against the archaea because the archaea do not have peptidoglycan. And so if there ever is a human pathogen which is archaea, the clinicians are going to be in a hard spot because there are not many antibiotics that will work against archaea. And like I said, hopefully when that day happens, well, there will be an archaea which causes human sickness. Hopefully that won't happen during my lifespan. And hopefully not during your lifespan either. All right, any question about any of that? So let's move on to the mechanism of action of the different antimicrobials. And actually, I think I can blow that up. Yes. And probably blow it up a little bigger and then scroll up there. There are differences, or the antibiotics, the antibacterial drugs, work in different ways to damage the bacteria cell. There are antibiotics which inhibit the cell wall synthesis, and that will be a lot of common antibiotics like penicillins, the cephalosporins, vancomycin, bacitracin, just to name a few. And what they're doing is they're actually harming the formation of peptidoglycan, and we'll talk about that in great detail when we're talking about the penicillins. So that's the first way an antibiotic can inhibit the cell, a bacteria cell, by inhibiting the formation of the cell wall. But there are antibiotics which also inhibit protein synthesis. Tetracycline is a common antibiotic that does that. Chloramphenicol and the macrolides do that. There are a few antibiotics that disrupt the cytoplasmic membrane. Really, the only one I'll talk about is polymyxin B, and that's a family of antibiotics. And what it does, it puts a hole in the cell membrane, or in the case of polymyxin B, can also put a hole in the outer membrane of a gram-negative cell. And that can, all of those holes can damage the cell and leak the contents out. There are a few antibiotics that inhibit the general metabolic pathway, meaning they're interfering in a metabolic pathway that bacteria have and eukaryotic cells do not have. And we'll talk about two of those, the sulfa drugs, like sulfonamide, and then trimethylprim. They're inhibiting bacteria pathway that bacteria have, and eukaryotic cells do not have that pathway. There are some drugs that inhibit DNA synthesis or RNA synthesis, the nucleotide analogs and quinolones and rifampin. We'll talk briefly about those drugs, and like I said, they inhibit DNA. The nucleotide analog is pretty simple. It's either a nucleotide that's an analog to the DNA nucleotides, but it's not a DNA nucleotide, and the bacteria will put it into their genome when they're undergoing DNA synthesis, and that will screw up the bacteria cell. And then the RNA nucleotide analogs are similar, except it's an RNA nucleotide. Any question about any of that? And then lastly, there's inhibition of the pathogen's attachment to or recognition of a host cell. And there are some drugs which do that. And we'll talk about why these drugs aren't used too much, because they do work, but you have to have the drug being 100% effective, meaning it has to block 100% of the pathogens attaching to the cell or recognizing the host cell. And if you only get one cell that is not blocked, you can get an infection. So they do have drugs like that, but like I said, they're not used that often because really the other antibiotics we have, they're just better. Any question about that? Like penicillin G, it works. Even if it isn't working 100% effective, it still works. Okay? Whereas these drugs, they have to be 100% effective for them to really work. And so they're not used very much as antibiotics. Any question about any of that? Okay. So we talked about all of that. Let's talk about targeting the cell wall in specific conversation. We're going to be specifically talking about penicillin, and specifically penicillin G, although we will talk about the entire family, because this drug acts by inhibiting the cell wall. And when a cell is growing, it's actively putting down its cell wall, and so all the members of the penicillin family, the bacteria have to be growing. They have to be synthesizing their cell wall. Otherwise, the antibiotic is not very effective. Any questions about that? And I'll explain why when we're talking about it. So if you remember, in the cell wall, it is made up of two sugars, NAG and NAM, and they just repeat one after the other. And then there's a row of them, and then there's lots of rows, and then there's planes of the rows, and they're connected together with short peptide links, cross links, and links going down as well. The eukaryotes don't have any peptidoglycan in their cell wall. So if we found a drug which inhibited peptidoglycan from forming in a bacteria cell, it would be really selectively toxic and harming the bacteria cell, and then leaving the eukaryotic cells alone. And so that would be a good and very effective drug, meaning very selectively toxic. And penicillin is actually such a drug. It inhibits the formation of these crosslinks here, the peptide crosslinks. And when they're inhibited, you will have a gap in the cell wall, which is normally cross-linked together. And in that gap, the cytoplasm can come out. And so water will move into the cell, and the cytoplasm can come out of the gap in the cell wall and then just keeps coming on out, sort of like when you're blowing up a balloon in a box. Well, once the balloon has reached the size of the edge of the box, you can't blow up the balloon anymore. But if there's a hole in the box, the balloon can protrude out of that hole. And that's what the cytoplasm does in the hole made in the peptidoglycan from the penicillin interfering with the crosslink. And then so the cytoplasm will just keep expanding out of that hole. And as more and more water moves into the cell, eventually that cytoplasm coming out of the hole will rupture. And then the cytoplasm will leak out of the cell, and that will kill the cell. Okay? Any questions about any of that? Why you need a growing cell is that a cell which already has its cell wall made, penicillin G, or any of the members of the penicillin family really, will not work, because what penicillin does, I've got a picture of that right here, is that what penicillin does is it gets in, and where the crosslinks are supposed to be, why isn't that shown here? It prevents these crosslinks from forming between the NAG and the NAM chains. So the penicillin, oh here it's showing, gets in between the NAG and the NAM, and then they prevent the crosslinks from forming. And that allows holes in the cytoplasm, and so, holes in the cell wall, and the cytoplasm can expand out of that hole. And as more water comes into the cell, the cytoplasm will expand further until it bursts. And that's how penicillin works. But if you already have your crosslinks made, meaning the cell wall is already made, then penicillin will not be effective, because it has to intercalate in between the peptide links and prevent the crosslinks from forming. Okay? So that's why penicillin needs to be working on a bacteria cell which is actively growing, where the cells are actively growing. And if the cells are static, the penicillin will not work. Now, usually this is not a problem, because if a patient has an infection, the bacteria are growing. But if you were to give them an antibiotic that, let's say, slows down the growth of the bacteria, and then you give them penicillin, the penicillin would not work when it's administered as the second drug, because the first antibiotic has already slowed down the growth of the bacteria. Okay? Any question about any of that? All right. So penicillin is an antibiotic that can be inhibited in its how effective it is by other antibiotics. And we'll talk a little bit more about that later in the lesson. Let's say that penicillin G, actually I will talk about that, that penicillin G is very effective on gram-positive cells because the antibiotic can get into the cell and then get into the cell wall and intercalate in between the NAG and NAM chains, preventing the crosslinks from forming. But penicillin G cannot get into the peptidoglycan of a gram-negative cell. Anyone want to take a guess as to why that might be?
They have two membranes.
Can you repeat that?
They have an inner and an outer membrane.
Yeah, they have an outer membrane on the outside of the cell wall called the outer membrane of the cell wall, and penicillin G cannot get through that outer membrane. And so if it can't get through the outer membrane, it can't get to the peptidoglycan. And so penicillin G and some of the members of the penicillin family, they are not effective on gram-negatives. And that's true of a whole range of antibiotics. Some of them are not effective on gram-negative cells because the bacteria they have an outer membrane, so the antibiotic can't get to the cell. Any questions about that? So penicillin G would not work on a gram-negative bacteria that was infecting a patient. Now, that's not true of the later members of the penicillin family, like carboxycillin and amoxicillin, and even ampicillin, which is one of the early penicillin members of the family. They can work on both gram-negative cells and gram-positive, but it's not true for penicillin G and penicillin V. They only work on gram-positive cells. And it's just because of that outer membrane of the gram-negative cell. All right, any questions about any of that? Let's talk about the penicillin derivatives. I thought I had a picture of that down here. Doesn't look like I have it, but I've got a link to it here. So this is showing you penicillin G and then a later penicillin, methicillin. Methicillin is a semi-synthetic. I think carboxycillin is totally synthetic penicillin. And I'll briefly talk about the terms, but you don't need to know these terms. A natural member of the penicillin family is one that a mold makes, and then we use it. Any questions about that? So a mold makes the penicillin G antibiotic, and then we can purify it and then use it. So it's made by a living organism. A semi-synthetic is one where a living organism makes it, and it's usually penicillin G that they make, and then humans modify it, usually by adding on side chains, like if you look at this molecule here and this molecule here, they're the same except for there's a side chain here and a side chain here. And so humans have put on these side chains, and the side chains give methicillin new properties that penicillin G do not have. And I'll talk about those properties later. But the point is that this is a later antibiotic, and actually mold makes it, and then humans change its structure. A penicillin that humans make in a lab, and they just make it from chemicals, and then they make it totally themselves, meaning no living organism has a role in making it. That's called a synthetic or a man-made antibiotic. Okay? Any questions about that? It's not something I'm going to quiz you on. I'm not going to ask you what's a natural penicillin and what's a semi-synthetic and what's a synthetic. But those terms are used, so you should learn them just because they are used. And it comes down to another question, and that is, what is an antibiotic? A textbook definition of what an antibiotic is a antibacterial drug, meaning a drug that's used against bacteria, that is made by another living organism. So penicillin G is, by that textbook definition, an antibiotic. But carboxycillin, which is in the same family as penicillin G, is not an antibiotic because it's made by man. Okay? Any questions about that? That's the textbook definition. And, you know, I've forgotten if a semi-synthetic is termed an antibiotic by the textbook definition, or if it's not an antibiotic by the textbook definition, because a semi-synthetic is made by a living organism, and then humans alter it. And that's the terminology of semi-synthetic. And I just don't remember the textbook definition for this because I've never cared about the textbook definition, because it's not the way that an antibiotic is used in general common usage by the population, meaning any member of the penicillin family is in common usage called an antibiotic. And that's the way most clinicians also use the term antibiotic, as an antibacterial drug. And it doesn't matter if it's man-made, like carboxycillin, which I'm not showing, or if it's penicillin G, which is made by an organism. And in this class, I will use the common usage for the term antibiotics. Any question there? All right. The point is that the different penicillins have this general structure that penicillin G has, but they will have side chains right here and right here. And this side chain can differ, and that's why we have different names. Okay, the side chains give them different properties, and I'll talk a little bit about that in a moment. All right, any questions? And so we've developed different members of the penicillin family, and they just differ on their side chains. What's important to all members of the penicillin family is this area shaded in green. This ring is called the beta-lactam ring. You should know that. And it is the active component of all of the penicillins. Okay? It's the component that stops the cross-linking from happening in peptidoglycan, that beta-lactam ring. And surprisingly, the beta-lactam ring is found in the cephalosporins. This is another family of antibiotics, but it has that beta-lactam ring as the active ingredient. And what all of the members of the cephalosporins do is they stop the formation of the cell wall by interfering with the crosslinks in the peptidoglycan. Any questions about any of that? And yes, they have made antibiotics, and all they are is the beta-lactam ring, and they are active as antibiotics, but they're not as effective as penicillin G or the other members of the family. So we tend to use a member of the penicillin family rather than just using the beta-lactam ring. Okay? Any question there?
Is cephalosporin found in molds or fungi?
I think the original cephalosporin, let me say this is a very large family. The cephalosporin family is even larger than the penicillin family. But the earliest members of the cephalosporin family were biologically made by some living organism, but I do not recall what that living organism is. Okay? Like with penicillin, I know it's the penicillium mold, and we'll talk a little bit about that. But cephalosporin, I know it's the early members of the family were made by a living organism, but I don't remember if that's a mold or if it's a bacteria. Okay? So is that a good enough answer? If it isn't good enough, I can look it up.
Oh, that's okay.
Okay? The later members are, like this one here, Cephalosporin. It is a semi-synthetic, meaning somebody's changed it, modified it, chemically modified it. And then some of the latest members are totally man-made for the cephalosporin. Like I said, it's a very large family. There's over 70 members of antibiotics in the cephalosporin family. And the penicillins, it's not as large. It's something like over 40, maybe even over 50 members of the penicillin family. And I could not tell you all the members of the penicillin family. And the cephalosporin family, I don't even know. I only know one, this one here. I studied this one a lot because we're going to talk a lot about penicillin and penicillin G in particular, but I don't talk about any of the other antibiotics in any great detail. I will simply talk about, how they're used, and I'll talk about the members of the family, meaning the whole family itself, not each member of the family. All right, I think that's it. I'm trying to show you the different members of the penicillin family, and I think we did that. Let's talk about how the penicillin was discovered. Remember that Alexander Fleming was the first person in the 1920s to discover penicillin, and actually how he discovered it was because he was a sloppy microbiologist, and when he was streaking his plate, he got a contaminant on the plate, which happened to be a contaminant of the penicillium mold, and that's with an M, penicillium, as opposed to penicillin with an N. And he noticed that when he looked at that plate, there was a ring around the penicillium mold that was inhibiting the bacteria. And he correctly deduced that something was coming out of the mold and was inhibiting the bacteria, and he gave it the name penicillin, after the name of the mold. Okay? And that first antibiotic was penicillin G. Now, if I have time, and I probably will have time, so I'll try and give you the story of penicillin and how it was developed, and the first clinical case, actually the second clinical case of penicillin, and how it worked and all that. And so I'll try and give you a history of that, because I doubt this will take all the time that I have. So I'll try and give you the study. It's just an interesting case study of penicillin. Anyways, he was never able to purify it good enough to get it to work in a patient, meaning all he was able to do in the 1920s was get a crude extract that the mold was growing in, and keep out the cells. He was able to filter it, but it wasn't anything you could give a patient. And he did show that crude extract was effective on at least the gram-positive bacteria. The later penicillins were then developed, and there were a few that were also grown by molds, like penicillin V. But most of the penicillins were developed by, they took penicillin G or penicillin V, and then they changed it, chemically modified it, mainly by adding side chains. And ampicillin was one of the early ones that they made. And then later ones like amoxicillin and carboxycillin were, the latest ones were totally man-made, meaning mold did not make it and then humans modified it. The humans made it directly. Oh, there's the thing I was talking about. So that did show the family members and then how it interferes there. All right, let's talk a little bit more about this side chain here. What the side chains do is they give a different property to the penicillin G. Some of the side chains, like the side chain on methicillin, gives the property to the member of the penicillin family so that they go through the outer membrane of a gram-negative cell. And methicillin can work on both gram-positive and gram-negative bacteria. The side chains also tend to give the penicillin molecule the ability to resist digestion by stomach digestive juices. Like penicillin G can be destroyed by your stomach. So this molecule will be digested by your stomach, and then it's not effective. Whereas when you have the side chain on methicillin and ampicillin, it prevents the digestion of the penicillin family member by the stomach. And so actually I think all of the penicillin family members except for penicillin G can be ingested because they have a side chain which prevents the digestion of the molecule. Okay? And what's one other property that they give? Sorry here, I'm drawing a blank here on what the third one is. Oh, I remember now. Yes, they can also, like methicillin, is resistant to penicillinase. That's an enzyme that cuts the penicillin G molecule, and I don't remember if it cuts it here or here, but it's one of those places. It literally cuts the penicillin G molecule in two, and that is called penicillinase or beta-lactamase, after the beta-lactam ring. And if you have a side chain on penicillin that prevents the enzyme from binding to the molecule, and then the enzyme cannot cleave the penicillin family member. Like methicillin is resistant to penicillinase. And as far as I know, although I'm not positive about penicillin V, but as far as I know, penicillin G is the only family member that is sensitive to the enzyme penicillinase. All of the later antibiotics, starting from ampicillin, which I think was the third one developed, are resistant to penicillinase. Okay? And like I said, the only one I'm not certain of is penicillin V, which was the second penicillin family member discovered. Okay, so that side chain is really different and gives the different properties to the molecule, meaning that if it has a side chain, it can be taken orally because the stomach digestive juices don't digest the penicillin molecule. It can allow the molecule to come into gram-negative cells, and the third thing is it can inhibit penicillinase. Any questions about any of that? How are we doing time-wise? We still have time?
It's 3:15.
Yeah. Thank you. So one of the mechanisms that bacteria can become resistant to penicillin G is to make an enzyme called penicillinase or beta-lactamase. And what it does is it cleaves the beta-lactam ring. So I got that wrong. I was thinking it cleaved it here, but no, it cleaves the beta-lactam ring, and then it opens up the beta-lactam ring, and now this is not effective. It's an inactive penicillin molecule. Okay? And so if the bacteria makes penicillinase, it will be resistant to penicillin G. As I stated, drug developers have made more members of the family, like ampicillin and methicillin, which have a side chain right here, or right here, which prevents penicillin from working. And they are resistant, methicillin and ampicillin, to the penicillinase enzyme. But bacteria have developed other ways to becoming resistant to the penicillin family member. Like methicillin, there are bacteria that are now resistant to methicillin, and an example would be MRSA, multi-drug resistant Staphylococcus aureus. It is resistant to methicillin as well as to penicillin G, and it's developed a resistance to methicillin by some other means, not by penicillinase. Okay? And that's why oxacillin was developed, because bacteria were becoming resistant to methicillin. And so the drug developers made oxacillin to replace methicillin because the bacteria were becoming resistant to methicillin. And you can see drug developers are continuously in this war where they have to stay ahead of the evolution of drug resistance. As the bacteria become resistant to the first antibiotic, penicillin G, they made ampicillin, which was resistant or was not, penicillinase was not effective. But then the bacteria became resistant to ampicillin by other means. And so the drug developers made methicillin. And then the bacteria started becoming resistant to methicillin. So the drug developers made oxacillin. And there's this kind of like an evolutionary war where the drug developers have to stay ahead of the resistance to drug resistance. And if they don't stay ahead of it, then we won't have an antibiotic that will work on the infection. And as you know, we ran into that lately in the last, about 15 years, maybe even longer, but about 15 years, we've found some infections which the infective agent is resistant to all known forms of antibiotics. And then what do? Any ideas? You can't use an antibiotic because the bacteria is resistant to it. Then you have to use creative and elective methods, which aren't as good as antibiotics, but there are some treatments, like some patients who have a totally multi-drug resistant Staphylococcus aureus, or MRSA, or MRSA, which is resistant to all known forms of antibiotics. Well, you can put honey on the skin. There's 5 hospitals in the United States which have a virus that infects MRSA and then will kill the cells. And it's an experimental treatment, but there's 5 hospitals in the United States that can do it. And there's a few other treatments they have, but they're all experimental, and generally speaking, you have to go to the correct hospital to get that experimental treatment, meaning not all hospitals can do it. Any question about any of that? Okay, let's move on then. So, when a patient comes into the clinic and has a bacteria infection, the clinician has to consider a large number of factors, as well as what is an effective drug to apply and what might be the drug resistance. Clinicians have to consider other factors in deciding which drug to treat the clinician's infection. The first factor they will consider is the spectrum of action, meaning all drugs work only on a certain family or a certain spectrum of pathogens. And you can split the pathogens into different phyla, like the mycobacteria are different than the gram-negative bacteria, which are different than the gram-positive bacteria, and they're also different from the chlamydias and the rickettsias. These are bacteria which are pathogens to our cells, but they're not pathogens in the way that these cells are pathogens. These are pathogens that get inside our cells, and so the drug has to get inside our cells and then do harm to the intracellular parasite. Okay? And then there's protozoa, which are eukaryotic pathogens, and fungi, which are eukaryotic pathogens, and helminths, and then viruses. So each of these different phyla have drugs that work on them. And as you notice, there's no drug that works on everything. Any questions about any of that part? But there are drugs which are narrow, and they have a narrow spectrum of action. Like there's certain drugs that only work on viruses, certain drugs that only work on helminths. And we kind of stated, like penicillin G mostly works only on gram-positive bacteria. So penicillin G would be a narrow spectrum of action. Polymyxin B only works on the gram-negative bacteria, so it has a narrow spectrum of action. And then there's some drugs which we say have a broad spectrum of action. They work against several phyla, like the sulfa drugs can actually work on gram-negative bacteria, gram-positive bacteria, the chlamydias, and some of the protozoa. Okay, so very broad spectrum of action. And I suppose that's probably the broadest one. Don't ask me about streptomycin. Is that a broad spectrum or a narrow spectrum? It's sort of in between. It can be used on 2 different groups, the mycobacteria and the gram-negative. But erythromycin can work on 3 groups. Okay? Any question about that? Now, what drug, meaning a narrow spectrum of action or a broad spectrum of action, is one that would be better to use? Generally, if you know what the infective agent is, so you know an antibiotic that will work, then you use the narrow spectrum of action. And we'll explain why in a little bit. It'll be discussed in the next section, I think. No, 2 more sections from now. Okay, but generally you want to use a narrow spectrum of action if you know what the infection is being caused by. But oftentimes, when a patient comes in with an infection, the clinician isn't going to know what's causing that infection. Okay? in which case they have to apply a broad spectrum drug because they don't know, is it gram-negative or is it gram-positive? Any question about that? All right. So oftentimes they use a broad spectrum drug, and that's just because they don't know what it is causing the infection. The clinician has to decide on which administrator route to use. There are different routes that you can apply the drug through. Patients generally prefer a topical ointment that they put on their screen or taking the drug orally, but you can also take the drug intravenously, intramuscular, and that's similar on a shot. Intramuscular is into the muscle. Intravenously is you directly inject it into the veins. Or you can take the drug as an enema. Do I need to explain what an enema is to anyone? There are different reasons for taking a drug. The main purpose for choosing a route for administering the drug is just the ease of the route. Like most patients like to just take the antibiotics orally, so that's an easy way to do it. Generally, they're less likely to take the drug if they take it in a way that they don't like to take it. Like children, for example, if they're ever given the choice of getting a shot or not getting a shot, they're not going to get a shot. And actually, probably some adults are that way too. So the ease of the route has to be considered. And let's say you have a really fussy baby and it's constantly spitting up the medication you give to the baby orally. Well, an easy way to give a baby medication might be giving it through an enema. All right? Just because it'd be very easy to apply to a baby and the baby won't spit it up. And if you give the baby an intravenous shot or an intramuscular shot, a fussy baby will definitely not like that. Okay. Another consideration for the administrative route is how long the drug will stay in the person if they're administered in a certain route. For like example, I'm showing examples for penicillin G. If it is administered orally, it does last longer in the patient than if it's given intramuscularly or given intravenously, although we should really say when you're injecting it intravenously, it will climb very rapidly, but then it drops very rapidly. Right after the shot, it's going to drop. This intravenous is through a hospital bag intravenously, where it's delivered the tubing into the vein, and then it's a drip system which allows it to last a long time. The drip system is not really applicable to most patients unless the patient is in the hospital. There are some exceptions, but generally this intravenous system with a drip system that lasts a long time can only happen in the hospital, generally speaking. Okay? So normally, intravenously, when you just give a shot, it will climb very rapidly and then it drops very rapidly. So with penicillin G, we tend to give that medication orally. Actually, maybe that's penicillin V, because we give that one orally. And it lasts longer, but you'll notice that the drug getting into the blood of a patient when it's taken orally is not ever as high as when it's given intramuscularly or when it's given intravenously. So that's one disadvantage of giving orally. and that is you have to give the patient a high dose to make sure that the dosage will be high enough. But one nice good thing about orally is the drug lasts in the system longer than intramuscularly and then intravenously when you give a shot. All right? Any question about any of that? Let's finish this and then we'll stop early. We'll talk about the side effects. The side effects is definitely a major consideration for the clinician for deciding on what drug to give a patient. And that is, we want a drug which is safe, and actually what we would like is to have a drug that has no side effects. In reality, there is no such drug. All drugs, even the ones that are very safe, like penicillin G, they do have at least minimal side effects. And the reason that all drugs has at least minimal side effects is that the drugs will disrupt your normal microbiota. So when you take any antibiotic, yes, it will disrupt the pathogen that's causing the infection, but it's also going to disrupt your normal microbiota because you have a normal microbiota which is gram-negative and some which are gram-positive, and whatever drug you take, it will affect one or the other, and if it's a broad-spectrum drug, it will affect both of them, okay? And so when your normal microbiota is thrown out of whack, that can give you side effects. And so normally, when we give a drug, the patient will have side effects, and hopefully the side effects are minor, okay? But yes, a possible side effect could be death. Any questions there? Now, usually when we give antibiotics, unless the patient comes down with an allergic reaction to the antibiotic, death is not usually one of the side effects. But when we're giving like chemotherapy to a cancer patient, death is definitely a possible side effect. Okay? Any questions about that? And when you give any antibiotic, it will disrupt your normal microbiota. And that's why we want to use a drug that, if you know what the infection is, you want to give a narrow spectrum of action drug, if you can, because it will give you less side effects than a broad spectrum drug. Any questions about that? Okay, if there's no questions, I think this is a good place to stop, and so I'll stop here where we will talk about the mode of action for the drugs. And I will see you next Monday. Remember, you have to take the quiz this Friday. You should be able to take it at midnight tonight, anytime till 11:59 p.m. on Friday. All right, any questions? If not,